Hi everyone, this is Mr. Bowman, and in Chapter 5 we are going to talk about areas under curves, or areas between curves and the x-axis. So we're going to start out with a simple example here about a train moving along at a steady rate of 64 miles per hour from 7 a.m. to 9 a.m. In the first part, we are going to graph the velocity of the train, and so as you know, we have a horizontal line here with a height of 64, and the velocity is in units of miles per hour, and it travels from 7 a.m. to 9 a.m. So 7 a.m. is going to correspond to t equals 0, so 0, 1, 8 a.m., 9, or 2, 9 a.m. And that is it. The time would be in units of hours. In part B, we are asked to find the total distance traveled during those 2 hours. So as you know, to find the distance, we are going to take the velocity, which is 64 miles per hour, and multiply it times the time that it was traveling at that velocity, which is 2 hours, and that's going to give us 128 miles. Now, how is that related to an area under a curve? Well, if you look at the graph above and you draw a vertical segment to form this rectangle here, the height of that rectangle is 64 in miles per hour, and the length of that rectangle is 2 hours. So if you were to multiply those two, the hours would cancel out and give you 128 miles, but that is also the area of the rectangle, or the area between the curve and the horizontal axis. So the distance is represented by this area. Again, this is a very simple example, but the concept applies to more complicated examples like the next one here, if you had a velocity that was not constant but was changing, and it was an interval from time A to time B, and we wanted to find the distance. We would take the total area between the curve and the x-axis, and that area would be the distance again. And this doesn't only apply to velocity and time, it applies to other examples as well, which we will get into. So the big question here is, how do you estimate those areas when you don't have a nice geometric shape that we know the formula for? Here's an example below. The particle starts at x equals 0 inches along the x-axis, with velocity v of t being equal to t squared for time greater than or equal to 0. How far has the particle traveled after 3 seconds? So again, if we were to find the area between the curve and the horizontal axis, that area would represent the distance traveled. Now, in this case, you might do something relatively simple, like saying that the distance, which is equal to the area, is approximately, in this case, the area of the triangle, so 1/2 times the base of 3 times the height of 9, and half of 27, or approximately 13.5, and in this case the unit would be in inches. That would be one way to estimate that area. But in that case, you would be assuming that you have a triangle when in reality you don't, so your estimate would be an overestimate in this example. So we're going to talk about some ways to estimate these areas, and they are called rectangular approximation methods. And the first one we're going to start out with is called the left rectangular approximation method. And basically what we do is we break the area under the curve into rectangles. Now, why do we call it the left rectangular approximation method? Well, because the height of the rectangle is going to be based on where the rectangle hits the function on the upper left-hand corner. So in this example, it says use 6 partitions, which you will notice is abbreviated LRAM, or left rectangular approximation method, subscript 6. So since we are going from time 0 to time 3, what we're going to do is we are going to have 1/2 second increments, and that will break that up into 6. So if we draw the first increment here, it is going to, the left-hand side is going to have a height of 0, and then the next one, the left-hand side, is going to have a height corresponding to whatever the value of the function is at t equal 1/2, and then the next one is going to have a height corresponding to the value of the function at t equal 1, and t equal 1.5, and t equal 2, and t equal 2.5, and so on. And if you count the rectangles, you will see, even though the first one has an area of 0, there are 6 rectangles. So the distance in this case is approximately equal to the width of the rectangle. Each of these rectangles are 1/2 second wide, times the corresponding height, which is based on the upper left-hand corner of the rectangle. So 1/2 times v of 0 plus 1/2 times v of 1/2 plus 1/2 times v of 1, and so on and so on and so on, until we get to 1/2 times v of 2 and 1/2. And if you do the math on that, that turns out to be 1/2 times 13.75, which turns out to be 6.875 inches. Very often you're asked, is this an overestimate or an underestimate? You can clearly see that the total area of all those rectangles is less than the total area under the curve, so this is an underestimate. One of the things I'd like you to think about as you're looking at these is, under what circumstances are these 3 methods that we're going to learn about, LRAM, MRAM, and RRAM, either overestimates or underestimates? So the next method we're going to take a look at is the same idea, except we're going to establish the heights of the rectangles based on the upper right-hand corner of the rectangle, and that is called RRAM. And just to make the comparison simple, we are going to use 6 sub-intervals, so 1/2 second intervals from 0 to 3. And we use the right-hand side of the rectangle to establish the height. So the first one is going to be v of 1/2 as the height, and then v of 1 as the height, and v of 1.5, v of 2, and so on, and so on, and so on. Take your time when you're drawing these rectangles and make sure you're using the correct method, either MRAM, RRAM, or LRAM. So again, we have 6 rectangles. Each rectangle is 1/2 second wide, and the distance that the particle travels can be approximated by the sum of the areas of those rectangles, which is going to be 1/2 times v of 1/2 plus 1/2 times v of 1 plus ... all the way up to and including 1/2 times v of 3. And it turns out that that is 1/2 times 22.75, which turns out to be 11.375 inches. So think for a minute whether or not that's an overestimate or an underestimate, and think again under what circumstances you would have an overestimate or an underestimate. This is clearly an overestimate, as you can see that the area under the curve is less than the total area of all the rectangles. And the last method that we're going to talk about is called MRAM, and that is for midpoint rectangular approximation method. So we'll start out by dividing the 3-second interval into 1/2 second subintervals. And this one's a little bit trickier. You need to estimate where the height of the rectangle is at the middle of each of those intervals. So it might help by just drawing a point on the curve in between the endpoints of those subintervals, and then use that to help you establish the height of each of the rectangles. And it's not so important that you get the picture absolutely accurate, but the calculation needs to be. So in this case, we are going to have our first height is going to be at v of 1/4, and since we're in half-second increments, the second one, its height is going to be at v of 3/4, and so on and so forth. So the distance in this case is approximated by 1/2 times v of 1/4, or v of, we'll do it in decimal form, v of 0.25 plus 1/2 times v of 0.75 plus 1/2 times v of 1.25, and you keep adding and adding and adding until you get to 1/2 times v of our last one, which is going to be 2.75. And it turns out that that is equal to 1/2 times 17.875, or 8.9375 inches. And this one, well, we're not really sure if that's an over or underestimate. We'll come back to that. So at this point, I want you to pause the video for a moment and think about how you would answer these two questions. If a continuous function is increasing on the closed interval a, b, what is true about using LRAM to approximate the area under the curve, and what about using RRAM? Basically what I'm getting at here is LRAM going to be an overestimate or an underestimate, and the same thing with RRAM. And what if, in the second question, what if the function is decreasing on the closed interval? Will LRAM underestimate or overestimate? What about RRAM? Pause the video, think about that for a minute, and then when you're ready to see the answer, continue on. Before we answer the two questions, we're going to go back and look at this example where the velocity was continuous and increasing on our closed interval. And you can see that LRAM is an underestimate. On the other hand, RRAM was an overestimate. We're not going to talk about MRAM at this point. As a matter of fact, we don't know. So it turns out that if we have a continuous function increasing on a closed interval, LRAM is going to underestimate the area and RRAM is going to overestimate the area. If, on the other hand, the function is decreasing on the interval, then LRAM is going to overestimate the area and RRAM is going to underestimate the area. My advice would be, don't memorize these. Draw yourself a quick picture and then sketch some rectangles using either LRAM or RRAM to answer those sorts of questions. Very often when you are seeing these rectangular approximation methods problems, you're going to see the information given in a table, and another thing that you are going to see is you're going to see subintervals that are not equal in length. So don't just assume that the subintervals are always going to be the same or that you're going to have a graph to work with. So in this case, you can imagine the velocity being on the vertical axis again, so v of t, and time being on the horizontal axis. So if we are going to use this data in this table to answer these questions, we have to pay attention to how we're going to do this. So in part A, it says, estimate the distance traveled by the object in the first minute of movement using LRAM and RRAM. How many partitions should we use? Well, let's just make this simple and count off how many intervals we have. So I'm drawing these markings here on the left-hand side, and as I count that out, we have 6 intervals. So we are going to use 6 sub-intervals, so to speak. But at the same time, you will notice that the intervals are not the same length. 0 to 20 is 20 seconds, 20 to 30 is 10, 30 to 50 is 20, 50 to 70 is 20, 70 to 80 is 10, and 80 to 120 is 40. That's okay. We do not have to have rectangles that are the same width when we do this, and in this case we can't. So LRAM with 6 subintervals is going to use the width of the interval, so first interval 20, times the height of the rectangle at the left-hand side, which is going to be the value of the function. So in this case, it's going to be 20 times 0 plus the next interval is 10 units wide times 44 plus the next interval is 20 units wide times 15 plus the next interval is again 20 units wide times 35 plus 10 times 30 plus 40 times 44. And that turns out to be 3,500, and the units would be meters per second times seconds, so meters. Similarly, RRAM is going to use 6 rectangles, but in this case, we're going to use the same intervals, so 20, but we're going to use the height of the rectangle on the right-hand side if we were to graph this. So 20 times 44 plus 10 times 15 plus 20 times 35 plus 20 times 30 plus 10 times 44 and finally 40 times 35. And if you were to work that out, you would see that you get 4,170 meters. So one of the questions that might arise would be, are these estimates using the rectangular approximation method either overestimates or underestimates? And you might be lulled into thinking you can answer that question in this case because it appears that the velocity is generally increasing. But there are some exceptions to that at the very end here. But even more importantly is you don't know what's happening to the velocity in between the endpoints of these subintervals. So for the first subinterval at time 0, the velocity is 0, and at time 20, it's 44. You can't assume that the velocity is constantly increasing on that interval. It could be up and it could be down. Is it possible to use MRAM to estimate the distance traveled? Well, that kind of gets back to what I just said. You don't know what the velocity is at the midpoints of these intervals, so the answer to that question is no. So we're going to finish up with a couple of examples here, and then we will work on homework in class. So here's an example. Water is removed from the tank at a rate modeled by R of t liters per hour. where R is a differentiable and decreasing on the closed interval from 0 to 8. Selected values of R of t are shown in the table below. Estimate R prime of 2. All right, as always in this class, you really have to pay attention to the questions that are being asked. And in this case, we are not estimating the total liters that are going to be drained out of the tank over a 2-hour period. What we're asking is to estimate the derivative, the rate of change of R of t at time equal 2. So we don't know the exact value of R prime of 2, but what we can say is that R prime of 2 is going to be a slope. It's the slope of the tangent line to R of t at time 2. Since we don't have a time of 2, what we're going to do is we're going to pick the two closest times that we can, which are 1 and 3 hours. And so R of t, R prime of 2 is approximately equal to the slope of the secant line. That's the best that we can do to estimate this. So 950 minus 1190 over 3 minus 1, or negative 70 liters per hour, the numerator, over hours, or liters per hour squared, negative 70 liters per hour squared. Again, that's the rate of change of R of t, not the total amount of water that is removed from the tank at time 2. In part B, on the other hand, it says use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during 8 hours. Is this an overestimate or an underestimate of the total amount of water removed? Give a reason for your answer. Okay, so first of all, a little vocabulary. A Riemann sum is what we've been doing in this lesson. It is estimating the area under a curve using geometric shapes or sums of geometric shapes. So it says to estimate using 4 subintervals, use a left Riemann sum. So we're going to use LRAM, left-hand rectangular approximation method, with 4 subintervals. And we're going to have to pay attention to our intervals here. So our intervals from 0 to 1 are 1 unit, 1 to 3, 2 units, 3 to 6, 3 units, and 6 to 8, 2 units. Again, they are not equal in width. So our rectangles, if you were to visualize this, are not going to be equal in width. And we are using the left-hand rectangular approximation method. So we're going to use R of 0, R of 1, R of 3, and R of 6. All right, so here we go. The first rectangle would be 1 unit wide times a height of 1,340. The second rectangle would be 2 units wide times a height of 1,190. Third rectangle is 3 units wide with a height of 950, and the last rectangle would be 2 units wide with a height of 740. And this gives you a total of 8,050, and that would be liters per hour times hours, or liters. The second part of that question asks whether or not it's an overestimate or an underestimate of the total amount of water removed. So if you go back to the stem of the problem, it says R is differentiable, which means it's continuous, and it says it's decreasing. Earlier I said I wouldn't try and memorize this. I would just draw myself a quick graph of something that is differentiable or continuous and decreasing, and use LRAM and think about the example, and you can see that the total area between the x-axis and the curve is less than the sum of the areas of the rectangles. So this is an overestimate because R of t is continuous and decreasing on the closed interval from 0 to 8. And that is it for today.